Hello, welcome to lesson 2 of my USA Biology Olympiad course. So, lesson 2 is where the textbook actually starts like talking about like actual chemistry and biology. Um, so you may be wondering why is there so much chemistry in a biology textbook? So, one of the phrases that I really like is that biology is just chemistry in disguise because you'll come to find that a lot of the stuff in biology is just chemistry stuff but reformed in like a biological context. So yeah. Okay, so the first concept that you need to understand for this chapter about the chemical context of life is basically everything around you is made of matter, which is made of atoms, which are made of elements. And basically, elements are just the different types of particles that you can have. So I'm assuming that if you're taking this course, then you probably already know enough about chemistry, like just elementary level chemistry, that you can understand this stuff. So basically, an element is a substance that cannot be broken down to another substance by chemical reaction. So it's basically the smallest level that you can possibly have. And then there are also compounds, which are basically just made up of two or more elements, just like fixed, like connected together. So I'm sure we all know the periodic table of elements. That's basically every single element in existence that we've discovered so far. And that's below here. And so there are 92 natural elements. Basically, these are elements that we did not make in a lab. They're naturally occurring. And of these natural elements, about 20 to 25% of them are actually important to the human body. So, or just to life in general. So basically, this is a really nice chart here. So these elements here are basically all the elements that can be found inside the body, like the important ones. And below here are just a ton of different elements that are found in as trace elements, so like they're barely in our body. And so this is a really nice chart. You don't need to memorize it, but I think it's really like just important to like understand conceptually, like, you know, just how much of our body is like each thing made of. Like we're mostly oxygen, carbon, hydrogen, nitrogen, that stuff. And yeah, but there is one thing to note that some naturally occurring elements are toxic to organisms. So, I mean, like there's a lot of them you can list. I know arsenic is one of them. It's really toxic. There's a fun fact actually that in the 1800s they would use arsenic to make the skin pale because arsenic literally killed like the melanin cells. So yeah, but there is a case study that basically there are some organisms that have evolved to who have evolved to not have a toxicity to these elements. And specifically, there's like flowers that can grow inside soil that would be usually toxic to other flowers. So I think that's really interesting. Okay, so the next concept is a bigger concept. It's about atomic structure. So most of this stuff should be technically a review for you if you know anything about like middle school chemistry. So basically, elements are also known as atoms. So like I said, everything is made up of atoms. And atoms have three different subatomic particles that make up an atom. So there's the neutron, the proton, and the electron. So basically, the proton is what identifies an atom. Like that's what gives the atom, like that's what makes an atom like the specific element that it's associated with. And you base that off of the number of protons you have. And then the neutron is just there to add mass. The mass of an atom is calculated with AMU as the units, atomic mass units, or you could call them Daltons. And so yeah. And then lastly, there's electrons, and these electrons give the atom its charge. Because remember that most things that have like a charge to them, like it's either positive or negatively charged. And so basically, um, the proton and neutron are both one AMU or one Dalton each, while the electron has mass but it's negligible. I mean, once you get to an advanced point, you start calculating with it, but right now it's like barely comparable to like the proton and the neutron. And so you calculate atomic mass by adding together the number of protons and the number of neutrons to get like a number of AMU or Daltons. And then you calculate atomic number by just counting up the number of protons. So the atomic number is what is the identifying factor of an atom. And so like say like the atomic number 3 is lithium. And so basically every atom that has 3 protons is lithium. Um, So yeah, and then usually in neutral atoms are pretty rare. I mean, they're idealized, and so basically in neutral atoms, the number of protons and the number of electrons are the same, and then the number of neutrons, yeah, the number of neutrons is like, it's by itself. It's like yeah, it's a different thing. And so basically, it's important to note that like on the periodic table, it tells you like the atomic mass and stuff. That's the average atomic mass. So basically, they used percentages like, um, yeah, I'll just go into isotopes. So basically, isotopes are elements that have um, a different number of neutrons than they usually would than a neutral atom. So basically, they're different forms of the same element with different masses. So basically, the atomic mass that's given in the periodic table is just all of the isotopes that exist in nature averaged up based on their percentage. So yeah, and for example, you have carbon 12 and carbon 13. So they're both carbon, except carbon 13 has one extra neutron, and these atoms can get these neutrons from just reactions or like collecting them. And basically, there are some types of isotopes that are unstable. Obviously, you can't have like, I don't know, like 6 protons and like a million neutrons. That becomes incredibly unstable and it's like unbalanced. So that's where radiation is. It's basically once an isotope becomes unstable, it starts decaying and releases radioactive energy. And so that's what a radioactive isotope is. So in science, you can use radiation to find a lot of things. Specifically, there's a process called radiometric dating. So you may have learned about this in math class, or I'm in calculus right now, so I learned about it in calculus. But basically, you calculate radiometric dating with this specific formula. It's an exponential formula, but so radiometric dating uses the idea of half life. So half life is the amount of time for half of a given mass of a element to decay, of a radioactive element to decay. So for example, the half life of uranium 235, I think, or 238, I forgot, is 4.8 billion years, I'm pretty sure. And so that basically, say you have like 100 grams of uranium, after 4.8 billion years, it would have decayed to 50 grams. And when I say decay, I just mean it like falls apart, you know. And so you can use radiometric dating to calculate like the life, how long something has existed. You can use carbon dating. That's how people found out like how old fossils are. They use carbon dating. And so yeah. So another thing about atoms is that there are multiple shells, and these shells are basically where the electrons reside. So technically in actual atoms there aren't actual cells. Like this model of the atom here is a very idealized model. This is not actually what an atom would look like. For one thing, like the nucleus, oh yeah, I forgot to mention the nucleus is where the protons and the neutrons reside, and so they're all in the very center of it. So the nucleus is a lot smaller, and then the distance between everything is a lot bigger. It's like magnitudes of size bigger. Like the nucleus is really small in comparison, and basically, electrons exist. Like you can never calculate what where an electron is. You never know where an electron is. Like it's basically impossible with our current technology. So basically, these shells are just regions where like an electron might exist, and that's like where we classified it. But basically, shells are basically tiers, and the more outer shells you go, the more energy you acquire, the more potential energy you acquire. And so there's this idea of basically in nature, we basically want to go toward the area that has the least potential energy. That's why, like when you're higher up, you have more potential energy, and then gravity pulls you down. So then you lose the potential energy of being high up. Um, and basically, so the electrons on the outer shell of the atom is more keen to reach the nucleus because the closer to the nucleus, the less potential energy they have. And so you can think of like these electron energy, like these energy levels, or these electron shells and their levels as like a staircase. You're falling down the stairs. That's in terms of energy. And so basically, the atoms on the last the electrons on the last shell of the atom are the ones with the highest amount of energy, and these are called the valence electrons. And basically, these determine how the atom interacts with its nearby atoms. So let's just use the example of like sodium and chlorine. So sodium has um, one electron on its outer shell, and then chlorine has seven electrons on its outer shell. So you need to memorize the number of electrons on the outer shells. So just memorize it like 2, 8, 8, 14, I think, and basically that's like just the amount of electrons in each shell. And so these atoms want to, when they bind, they want to complete their shells. And so, obviously sodium and chlorine are going to have a great affinity to each other. And you'll also come to find that basically the closer an atom is to filling their shell, the more volatile they are. But once they actually fill that shell, they become like chill. And so sodium and chlorine are both very reactive elements, but once they bind together, they become an edible material. They become salt. So yeah. Um, okay, so as I was saying earlier, we never know where an electron actually is. So we created things called electron orbitals. So this is a three-dimensional model. I don't have a photo of it yet. You'll see it on the next slide. But basically, an orbital is basically we've come close to approximating where an electron might be 90% of the time. And so that area of where an electron might be is called an orbital. So you have actually, I'll just move on to the next slide so you can better see the example. So basically, in the center here, you have like a circle. It's not drawn on here, but that's called the 1s orbital. So basically, the one like s orbital is like two electrons, I'm pretty sure. And then, I mean, you can't know where these two electrons are, but like that's where they usually are. And so I don't think you need to really notice that much, but yeah, just like know that like each of these things have two electrons. And so that's like a shell. Yeah, interesting. So now this is concept 2.3. It's a really big two as well. It's molecules. So basically, there are two types of bonds that can exist between atoms. And so bonds are basically just when atoms are together. Like I said earlier, they're compounds kind of, but also molecules. And so the first one is a covalent bond. So basically, a covalent bond is when they're sharing a pair of electrons. So a pair of valence electrons. And so you can have a single bond. For example, let's take hydrogen and hydrogen. So each hydrogen has one electron. So they can share an electron and then they both get to fill their shell. I wish I had a better diagram with this, but just think of it like you can draw a circle, draw two circles, okay? And just like make it so that the two like rings of the circle just like touch at a single point. Think of that single point as the electron they're sharing, and then the other electron they have is just like floating around somewhere, I suppose. And so when they're sharing one electron, that's one bond. You can also have double bonds or even triple bonds where they're sharing more than one electron. And so it creates more bonds. And then the more bonds you have, the stronger the bond is, which is pretty self-explanatory. So basically, the bonding capacity of an atom is basically how many bonds it can have. So for example, oxygen can have a double bond, so its bonding capacity is 2. And that bonding capacity is also known as valence. So basically, there's also a concept called electronegativity. So electronegativity is the attraction of an atom for the electrons of a covalent bond. Like I said earlier, you can use Na and then Cl, so sodium and chlorine. Basically, they have really strong electronegativity because they're really close to filling their bond. And so, yeah. And lastly, there's an idea called polarity. Polarity is a little bit difficult to understand conceptually. But basically, just take a water molecule. We all know a water molecule is H2O, right? So you have an oxygen bond in the middle, and then you have two hydrogens on the side. So basically, water is a polar molecule because the oxygen is negatively charged, and then the hydrogens are positively charged. So you know that oxygen is, well, obviously a bigger element, and also it has more electrons. So the oxygen is gonna have like a more electronegative end, and so polarity is basically when a molecule has uneven like charges. Like you have a greater negative charge on the oxygen side, and then a smaller positive charge on the hydrogen side. So that like uneven charging is what creates polarity, and you can be nonpolar when the electronegative standoff is it's a standoff. Like there's not any unevenness. It's equal. So yeah. Okay, and then the other type of bond you can have is an ionic bond. So an ionic bond is when two atoms of unequal charge, um, they're attracted to each other because of their unequal charge. So we both know how magnets work. So we all know how magnets work. It's like the positive side is always attracted to the negative side. It's a similar thing for ionic bonds. So like the negative charged atoms are more attracted to the positive charged atoms. So if you know your periodic table, you know what elements are negatively charged. So yeah, just think of it like that. So a positively charged atom is called a cation, and then a negatively charged atom is called an anion. And so um, their cations and anions bond together with each other. And then so their charged attraction is called an ionic bond. And so these compounds of an anion and a cation are called ionic compounds, and they're also known as salts. So I kind of been lying in saying that NaCl is a covalent bond. I just think that it's easy to understand like that. But NaCl is actually an ionic bond because Na is very positive and Cl is very negative, and so it's mainly that attraction that connects them together, and that's why it's salt. It's like the basic salt. So yeah. Um, you can also use the example of Mg magnesium chloride. So you have two chlorides and one magnesium. You just connect themselves together. So yeah, like yeah. Um, so there's also an idea of weak chemical interactions. I forgot the weak, but basically these interactions aren't as strong as ionic and covalent bonds, but they're still like bonds. So you can have so there's hydrogen bonds. Hydrogen bonds are basically the bonds that give water its many properties. We'll talk about that next lesson with chapter 3 about water. But basically, water is like really special. It's a high boiling point, high specific heat, high surface tension, high heat of vaporization, and it has adhesion and cohesion, which basically means that it's attracted to literally everything and itself. So hydrogen bonds are basically just the bonds between hydrogen and an electronegative atom. Um, yeah, it's pretty simple. And then like yeah, that's just a bond. But it's a pretty weak bond compared to ionic and covalent bonds, but it's very special often, which is why water has such special properties. And then the other weak type of interaction is van der Waals interaction. So these are lesser known interactions, but basically, have you ever seen those geckos that like walk around and they can just like walk on walls like upside down or vertically without having to fear about gravity? Well, that's because on their hands there are specific like atoms on the very surface of it that allow it to have van der Waals connections, van der Waals connection. Basically, they're kind of like a sticky kind of connection. It's obviously really easy to break because you can just like pull like a gecko off the wall, but basically, they're kind of like really weak and individual um, interactions that occur only when they're super close together. Like these atoms are super close together. So yeah. And then lastly, molecular shape. So this is basically just like when you form like a molecule, the atoms are going to have like a specific shape. Let's take water, for example. I really should have included a water like diagram. But basically, you have the big oxygen and then you have the two hydrogen. So like I said earlier, it has polarity. So one side is negatively charged, one side is positively charged. So the oxygens are kind of like, instead of just being like think of like a circle and then two circles on the exact opposite sides of each other. The two circles are kind of clumped on one side. So those two little circles are the hydrogens. The hydrogens are kind of clumped on one side of the oxygen atom. So that atomic shape is bent. So yeah, think of it like that. And there are many different types of atomic shapes you can have just based on like the amount of bonds you have. You can have like tetrahedral, pyramidal, etc. And yeah, it's three-dimensional, and there's two different types of molecular shapes you can have. You can have like the shape of like a basic like visual like a basic bond that you can draw out kind of basically when you have the um, formula or equation, whatever it's called. And then there's also the shape that happens when you visualize it in 3 dimensions. So yeah. Okay. Lastly, there's chemical reactions. So basically, chemical reactions are just when um, two different elements or two different molecules react together and then form new products. So basically the starting materials of a chemical reaction are called the reactants, and then the resulting materials are called the products. So one really good example of a chemical reaction is photosynthesis. So a lot of us know what photosynthesis. I'm pretty sure most of us know what photosynthesis is. So the chemical reaction for it is you have six carbon dioxide molecules or moles, and then you have six water moles. And so basically, those are your reactants. You start with those, and then through the reaction, which is caused by sunlight and chlorophyll, which is basically the stuff that they call us like photosynthesis, you can get your products, which are carbohydrate and oxygen. So notice how basically in a chemical reaction, you need to make sure that all the stuff you have here is the same as all the stuff you have here, but just like in a different form. So you still have 12 hydrogen, you still have 6 oxygen, no, 6 carbon, and you still have 12 oxygen. So yeah, that's a really important thing. Obviously, you can't. We all know that you can't destroy or create matter. So just make sure they're equal. And then yeah, it's a chemical reaction. So there's also one thing that is called chemical equilibrium. So basically, this is when you have like two, say you have like two solutions mixing, and then they're having a chemical reaction. So every single atom of those solutions are going to be constantly reacting. So once you reach a certain point, you're going to have the forward and reverse reactions like becoming equivalent. So yeah, this is one concept I forgot to mention. In a chemical reaction, you know, when something happens, it can also happen the opposite direction. Like it can be vice versa. Um, Obviously not for like photosynthesis, but like you can use another like example like um, say like, oh yeah, hydrogen and nitrogen. So like if you have like three hydrogen plus two nitrogen, no, plus one nitrogen, you can have ammonia. And then so you can have, when you have hydrogen and nitrogen, that becomes ammonia. But also ammonia can also turn back into hydrogen and nitrogen. So, those two reactions are constantly happening in reverse motion. And then once you reach a certain point, the forward reaction and the reverse reaction happen at equal rates. So basically, in the end, nothing's changing at all. That's called chemical equilibrium because the reactions are still happening, but they're just basically unnoticeable. Nothing's like changing at all. And yeah, so yeah, that's the lesson. Yeah, it's a lot. Basically, a lot of it's just a lot of basic chemistry knowledge that, I think we should all know already because we all learned about this in elementary school. It's just you go more in depth. And currently, what the textbook is setting up is just the background knowledge you need to be successful in the advanced biology stuff, which will come later. But yeah, okay. When I actually have the course up, I'm basically done with the course website. I'll put it up soon. But yeah, when you're done with this lesson, just go take the quiz, look at the notes, slides, whatever you need, and yeah.